Good evening, everyone. Today we'll be discussing the contents of week 6 and some assignment questions pertaining to that. Uh, Previously, till week 5, we have seen what muscles are present in which parts and what movements they control and some problems pertaining to that. uh, this in this week there is instead of statics we have moved to kinematics, where we the look at a dynamic system where there is movement occurring and the results of those movements. So sorry. So uh, the first lecture showed reaching versus grasping versus manipulation, three different terminologies, and the process of grasping and the types of grasps that are there, uh, that are usually commonly considered, and in any analysis, and the kinematic chains. So coming to reaching versus grasping, reaching is, the definition says, the coordinated movement of hand and fingers towards the object that needs to be grasped. Say I want to hold on to this pen with this hand and I'm taking that hand here, that is called reaching. Whereas grasping is the act of actually holding on to the pen, wrapping the fingers around and supporting it with the palm. Uh, so this is basically the process, whereas this is the sort of the resultant move. Okay. Now uh, a grasp is uh, which is the resultant move, is a static hand posture, which basically is when you hold on to an object, what is the orientation of your hand in certain sets. Whereas when you differentiate it from manipulation, manipulation is operating the grasped object. You've already grasped the pen, then you are making changes in the orientation of your palm or your hand, and so that you can use that object in various for various tasks. So first is, suppose you need to write with a pen, the first uh, sort of movement is reaching, where you reach towards the object, then grasping, where you actually hold the object, versus manipulation, where you make orientation changes in your arm or in your palm, so that you can use the particular object that you have grasped in your hand. So manipulation is more of a dynamic process than, say, grasping is a static problem. Coming to the phases of grasping, there is a pre-grasp phase, where uh, it's the first phase when you are just about to hold on to a pen, for example. There's the grasp phase. The grasp phase follows the reaching phase, for example. Then there is the grasp phase when your fingers actually wrap around the object, and depending upon what you intend to do with the object, or what the object shape or size is, the grasp type changes. Then the final one is the manipulation phase, where the which constitutes the hand motions that result in the movement of the object. Uh, so these are the three phases that finally result in grasping. Now coming to types of grasp, there is a power grasp and there is a precision grasp. Uh, and usually precision grasp is used for smaller objects, things which require a certain control. Power grasp includes cylindrical grasp, hook grasp, lateral pinch. Cylindrical when you are, say, holding onto a bottle, hook when you are hooking your fingers into something, lateral pinch when you are trying to move a key within the keyhole. Precision grasp includes pinch, tripod, and circular. Pinch type of precision grasp is usually employed when you are holding onto a pen, whereas tripod is usually employed when you are using three of your fingers. Suppose you are holding onto a conical thing or a pyramidal thing. Circular precision grasp usually is employed when you're holding on to a ball or something, or some other spherical object. Now, these were the types of grasps, and depending on which kind of grasp it is, the analysis was going to be different. Next, coming to kinematic chains, which basically the simplest one is a kinematic pair, and following and as the system becomes more complicated, uh, it is called as kinematic chain. So in a kinematic pair, there is two rigid bodies connected by a joint between them. So this is the first rigid body, and this is the second rigid body, and this is the joint that connects them. For example, this might be your thigh, and this might be the uh, shank or the shin, and this is the knee joint, or this can be the elbow joint, and this is the lower part of the arm, and this is the upper part of the uh, this particular system is called kinematic pair, where there is two rigid bodies, and by rigid bodies the assumption is that they undergo no deformation upon if forces are applied on it. They're not elastic. Next is if there are more rigid bodies associated with a system, with more rigid bodies, the given is that the joints also increase. In that case, you observe a kinematic chain, which is an assembly of rigid bodies and links connected by joints in order to perform desired motion under a set of constraints. So the general rule is that the kinematic chain can have n number of links, and if it has n number of links, it will have n minus 1 number of joints. Okay, suppose for this particular setup there is 1, 2, 3 and 4, so 4 links. There is the joint 1 is between link 1 and link 2, joint 2 between link 2 and link 3, joint 3 between link 3 and link 4. So 3 different joints. Okay, so we learned about reaching, grasping, manipulation, and the processes that finally result in grasping, and the types of grasps and the kinematic chains associated with it. Next, let's look at degrees of freedom, which refers to the number of independent coordinates to completely characterize a body or a system. So if something is moving in one plane, it can, so anything that moves can have two types of degrees of freedom: rotational and planar. Rotational degrees of freedom is along an axis, whereas planar is along a plane. Okay, if you were to consider a XYZ coordinate system, rotations might happen in along y-axis, z-axis and x-axis, whereas planar movements might happen in XY plane, XZ plane or YZ plane. Okay. Now coming to the mobility of a kinematic chain or a mechanism, the mobility is defined by the number of degrees of freedom that might be present in a system, which basically can help it move uh, when given sufficient number of inputs. So the formula is m is equal to 3. M is the degrees of freedom, 3 times n, which is the number of rigid bodies or links in the mechanism, minus 1 minus 2 times j, which is the number of joints in the mechanism consisting of only single degree of freedom uh, kinematic pairs. So the assumption is that if this is a joint, it will only have 1 degree of freedom. Basically, in the end, it can be assumed that every joint acts like a hinge joint with no hyperextension. But just an assumption to make things simpler. Okay. And this particular equation is known as Kurzbach equation. Okay, so now we know how many mechanisms, how many degrees of freedom might be present in a mechanism, and most mechanisms have a single degree of freedom. But there might be mechanisms which have multiple degree of freedom, but these are the most these are more simpler. If there are if there is 1 degree of freedom in a system, you can find the relationship between the number of joints and the number of links, which is called as the Grubler criterion. Assuming that there is 1 degree of freedom, you can either compute the number of joints, which is 3n minus 4 by 2, or given the number of links, or you can compute the number of links, which is 2j plus 4 by 3, if the degrees of freedom is 1. This is a very important part. Okay, so we now know how many degrees of freedom are there. What are the different kinds of kinematic chain that one might encounter while solving a problem or analyzing a problem? There are 2 kinds. One is known as an open kinematic chain, and the other one is known as a closed kinematic chain. In the open kinematic chain, one of the end, which is usually the distal end, so this is the proximal and this is the distal end. The proximal end is usually fixed at a point, so if it's an arm, it's fixed, whereas the distal point, which is the hand, is free to move around. So basically, one end of the chain, mostly the distal end, is free to move, and there is a constraint imposed on the other end. The second type is a closed kinematic chain, wherein constraints are imposed on both the ends. This might be proximal and this might be distal. Okay, but there is constraint imposed on both the ends. Suppose you are standing at a place, then this is your, say, hip bone, and this becomes ground. Okay, and this particular chain is in robotics or mechanics. This open kinematic chain is known as a serial kinematic chain, serial manipulator, and this is known as a parallel manipulator. And these terms might be used interchangeably as we go along. So there are kinematic chains. They might be of 2 types, open and closed. But there are, apart from these constraints, there are other anatomical constraints that might hinder the kinematic chain. The constraints are joint limits, wherein, say, a hinge joint won't hyperextend, or suppose there is no hyperextension, there is no movement apart from whatever is allowed by the, if you look at the degrees of freedom and you say find 3 degrees of freedom, there are no movements in a 4th degree of freedom. uh, the other constant is the muscle plus tendon length. uh, remember there are different kinds of muscles, isometric and all of those kind of muscles, wherein there was here the assumption is that muscle plus tendon length is same. So if this is L1 and this is the muscle which is L2 and this is inserting somewhere else L3, L1 plus L2 plus L3 is constant. Okay. Next, there might be motion. So these things might limit how might be considered as anatomical constants as to how much movement is allowed in a particular kinematic chain. Then there are motion constants, wherein in which friction and body balance comes into play. There are external constants such as obstacles or walls or ground. Okay. Next, so again, sorry, excuse me. So we saw that kinematic chains are two types, open and reduced. Assumption here we'll be looking mostly at open kinematic chains. And the simplest kinematic chains either have 2R are called 2R or 3R, and R refers to rotatory joints. And usually the assumption is that these chains are consist of only rotatory joints. So whatever rotation happens in the plane that we are looking at. So if this is the rotation, then everything happens in this XY plane. Nothing is happening in Z plane. So the position analysis comes in two forms. Either you find the location of the endpoint using the joint angles, which is known as forward kinematics, which is when if you want to find x comma y and you have theta 1, the lengths L1, L2, theta 2, then you can compute x comma y, the coordinate of the final point of the endpoint, which is in this case P, using all of this information. Now the other problem that usually is performed is finding the joint angles using the endpoint location. So you are given x comma y, you have L1, you have L2, you need to compute here theta 2 and theta 1. So here the unknowns are x comma y and here the unknowns are theta 1 and theta 2 in our 2R problem. In a 3R problem, x comma y remains the same, whereas there is an additional theta 3 aspect, which is basically this angle. So theta 1, theta 2 and theta 3 are the three things that you need to compute. Okay. So let's look at forward kinematics first of a 2R system, which essentially includes calculating the endpoint location using link parameters and joint angles. So link parameters are L1 and L2 and joint angles are theta 1 and theta 2. Wherein theta is the angle that AB, which is the first link, forms with the base, whereas theta 2 is the angle that BP forms with AB. So if this were to be extended, theta 2 is this. Okay. Let me just. Okay. So these are the knowns. What we need to find is xy, unknown. You know x1, y1, kind of. So if this is this particular and this particular length, you know, because you know L1 and you know theta 1. L1 would be this particular length will be L1 cos theta 1, and this particular length will be L1 sin theta 1. So your x1 comma y1 coordinate becomes L1 cos theta 1 comma L1 sin theta 1. So you know this. Now this particular angle that L2 forms with the horizontal becomes theta 1 plus theta 2. And so trigonometry, you need, if you find this and if you find this, y would be this plus this, whereas x would be this plus this. So this particular thing becomes L2 sine theta 1 plus theta 2, whereas this particular thing becomes L2 cos theta 1 plus theta 2. So you know this to be L1 cos theta 1 plus this particular place which is L2 cos theta 1 plus theta 2. Coming to y, you know this to be L1 sin theta 1 and this particular portion to be L2 sin theta 1 plus theta 2. So this is your x, y coordinate. Okay, so you now know how to compute x comma y given that theta, given L1, L2, theta 1 and theta 2. One more term that you might encounter is workspace, which refers to all the points in the plane where point P is able to reach. So L1 and L2 stays constant. If this were a straight line, this length will be L1 plus L2. If this were, if BP folded over at on AB, this particular length will be L1 minus L2 ka modulus, which basically ignores the sign because you don't know which, if AB is longer or BP is longer in this particular case. So if ABP, if this particular kinematic chain is undergoing any movement whatsoever, all of the values of the endpoints that such movements will result in falls in this particular area. Okay, and basically workspace refers to all the points that in the plane at which point P is able to reach. And so it essentially consists of two concentric circles. The middle one is the minima, whereas the outer one becomes the maximum. And the region between these two circles is the workspace. So minimum, maximum, and the region between is the workspace. The minimum radius becomes L1 minus L2 ka modulus, which is the minimum length that you might encounter in a kinematic chain. Suppose there is a folding here like this, whereas the maximum length that one would encounter is when the kinematic chain straightened out, which is L1 plus L2. Okay, now we know what is the what we get from a forward kinematic scale. Now coming to inverse kinematics, which is basically calculating the individual joint lengths using link parameters and endpoint position. So you know L1, you know L2 in a 2R system, you know x comma y. What you don't know, the unknowns are theta 1 and theta 2. So if this were your system, this will be theta 2, this will be theta 1, L1, L2, and this is x comma y. we know x is equal to L1 C1 plus L2 C2 C12. So okay, let me take a step back. So we saw here that x is equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2, and y is equal to L1 sin theta 1 plus L2 sin theta 1 plus theta 2. Let's assume cos theta 1 to be C1 and cos theta 1 plus theta 2 as C1 C2. Sin theta 1 as S1 and sin theta 1 plus theta 2 as S12. Okay, and we will use these terminologies in the while solving for the inverse system. Just so C1 is cos theta 1, C12 is cos theta 1 plus theta 2, S1 is sin theta 1, S12 is sin theta 2, theta 1 plus theta 2. Okay, so x can be written as L1 C1 plus L2 C12, and y can be written as L1 S1 plus L2 S12. Converting this becomes x minus L1 C1 is equal to L2 C12, and y becomes L1 S1 L2 S12. Squaring both the sides results in x. So this becomes x square plus L1 square C1 square, basically x square y square plus 2ab minus 2ab in this case, minus 2x L1 C1 plus y square plus L1 S1 square plus L1 S1 square minus 2x L1 S1 to y L1 S1 is equal to L2 C12 L2 square C12 square plus L2 square S12 square. So you can just rearrange terms, and C1 square plus S1 square minus 2L x C1 plus y S1 is equal to L2 square C12 square S12 square. Now this becomes 1, this becomes 1. So yeah, you end up with x square plus y square plus L1 square minus L2 square. You get the L2 to this side minus 2x LC1 minus 2y L1 C1. Now assume this particular to be A, this to be B, and this particular term to be C. This equals to 0. So you end up with something like this: A C1 B S1 plus C is equal to 0. Sorry, this becomes C, this becomes A, and this becomes B. Okay, now consider a triangle wherein A and B form both the arms. So this hypotenuse becomes A square plus B square under root. And if you were to divide this equation by A square plus B square under root, you get A by A plus B whole a square plus b square root over into c1, and you divide, keep it on in all of the denominators. Assume that this angle is psi, so a by root over a square plus b square is cos psi. B by root over a square plus b square is sin psi. So you can write this as c psi and this as s psi. So c psi c1 plus s psi s1 is minus, you get this term to this side, and so remember cos theta cos psi plus sin theta sin psi is equal to cos theta minus psi. So this one results in cos theta minus psi, and which is minus c a square plus b square. You now have cos theta 1 minus psi is equal to minus c by a square plus b square, which finally results, so this is this you can apply cos inverse on both the sides. So theta 1 minus psi is minus cos minus c by a square plus b square. Now remember psi was b, which is the opposite side by the adjacent side here, psi. So theta 1 is tan inverse tan psi is b by a. So theta 1 is tan inverse b by a plus cos minus c by a square plus b square. You can substitute terms into this and then finally put the resultant into this equation and find out what theta 2 is, and theta 2 comes out to be cos inverse x minus L1 cos theta 1 by L2 minus theta 1, because you know theta is cos theta 1. So if you are looking at the x expression, L x is equal to L1 cos x is equal to L1 cos theta 1 plus L12 cos theta 1 plus theta 2 cos theta 1 plus theta 2 becomes L1 x minus L1 cos theta 1 by L2. You apply cos inverse on both sides. Theta 1 plus theta 2 is equal to x minus L1 cos theta 1 by L2 cos inverse, and theta 2 is finally cos inverse x minus L1 cos theta 1 by L2 minus theta 1, which is what you get here. Okay, so we saw two-link planar chain, forward kinematics and inverse kinematics. Coming to a three-link planar chain, which is slightly more complicated because it has one extra link. Just a second. Coming to the 3R forward kinematics, wherein there is L1, there is L2, and there is L3. And basically Px comma y becomes your final result. If you were to, L1, for forward kinematics, L1, L2, L3, theta 1, which is the angle of L1 arm with the horizontal, no, the angle between L2 and L1, which is theta 2, and L3 and L2, which is theta 3. So, and you can predefine these terms. C1 is cos theta 1, S1 is cos theta 1, S1 is sin theta 1, C12 is cos theta 1 plus theta 2, S12 is sin theta 1 plus theta 2, and similarly C123 and S123. Now x1, since you know this theta, x1 becomes L1 cos theta 1 and y1 becomes L1 sin theta 1. And we know from the previous solution, x2, y2 can be written as L1 cos theta 1, L2 cos theta 2, L1 sin theta 1, L2 sin theta 2, sin theta 1 plus theta 2. Now, there is one more additional point where you need to add L3 cos theta 1 plus theta 2 plus theta 3 into the x term to get finally here, and y becomes, in addition to y2, so this is y2, this is x2, y2 plus L, so this becomes theta 1 plus theta 2 plus theta 3. So finally y becomes y2 plus L3, which is this length, sine of theta 1 plus theta 2 plus theta 3. So x can be written as L1 C1, L2 C2 C12, which is cos theta 1 plus theta 2, and L3 C123, which is cos theta 1 plus theta 2 plus theta 3. And similarly y can be written in this form. Okay, so we now know what exactly is the forward kinematics, where you get xy from all of the terms that you already know. Here the knowns are L1, L2, L3, theta 1, theta 2, theta 3, and the unknown is x comma y. Whereas in case of inverse kinematics, you need to find three terms basically, but the known is again L1, L2, L3 and x comma y. And the assumption in a 3R problem is that the sum of all the angles is known. Sum of theta 1 plus theta 2 plus theta 3 is known. So you also know phi. Whereas the unknown is theta 1, theta 1, theta 2 and theta 3. This is what you need to compute. Similar to what we did in the first, in a 2R problem, assume this term to be capital X and this term to be small x, capital Y. We know x and y in the respective terms, so we can write, sorry, that is a different method. Anyways, so you can write x as small x minus L3 C phi. So since C123, which is cos theta 1 plus theta 2 plus theta 3, C1 to 3 is cos theta 1 plus theta 2 plus theta 3. Now we know theta 1, theta 2 and theta 3 are phi. This is known. So we can write this as cos phi. And so this becomes C phi. So in all of the subsequent equations, instead of C1, 2, 3, we'll write C phi. So x, if you define a term x as small x minus L3 plus C phi, L3 C phi, it can be written as L1 C1 plus L2 C2. And similarly, y can be written as L1 S1 plus L2 S12. And you uh, do square both the stuff, both of these terms, and you finally get an equation like this. So if I can write it down, L1, sorry, x square plus, and add both the terms, is equal to L1 C1 plus L2 C12 whole square plus L1 S1 plus L2 S12 whole square becomes x square plus y square plus L1 L1 square C1 square L2 square C12 square plus 2x just a minute. Sorry, something went wrong. Okay, anyways, um so we can write x as x minus L3 C5, which is L1 C1 plus L2 C12, and we can write x minus L1 C1 as L2 C12. Similarly, we can write y minus L1 S1 as L2 S12. Squaring both the sides and adding them, we get x square plus L1 C1 L1 square C1 square minus 2x L1 C1 plus y square plus L1 S1 square minus 2y L1 S1 is equal to L2 square C12 square plus L2 square S12 square. Essentially, if you separate out the terms, minus 2x L1 C1 minus 2y L1 S1 plus L1 square C1 square plus S1 square is equal to L2 square C12 square plus S12 square. All of both of them become 1. So if you were to get all of the terms to one side, 2x L1 C1 minus 2 plus 2y L1 S1 minus plus L square minus x square minus y square minus L1 square becomes 0. Assume this to be small a, this to be small b, and this to be small c, like we considered in the 2R problem. And if you consider a triangle which has small a and small b as their arms, and the angle with the tan psi is b by a, essentially. So you similar to what we did then, so a1 ac1 plus bs1 plus c is equal to 0. A by root over a square plus b square c1, b by root over a square plus b square s1 plus c is equal to 0. Now a by, so this essentially becomes a square plus b square. So a by a square plus b square is cos psi c1 plus sin psi s1 plus c is equal to 0. This again becomes cos of psi minus theta or theta minus psi, and depending upon that you will get your. So here we considered this to be theta minus psi. Let's consider the same thing here. Theta minus psi is equal to 0, is equal to minus c. So cos theta minus psi becomes cos of minus cos inverse minus c a square plus b square. Theta becomes, and remember tan psi is b minus a, so psi becomes tan inverse b by a, tan inverse b by a plus or minus cos inverse minus c a square plus b square. Okay. Versus if this was to be theta minus psi minus c a square plus b square, get psi plus c by a square plus b square. Okay, so here is where plus and minus sign comes. Okay, in this case you get a minus sign, whereas in this case you get a plus sign here. Okay, so we saw two kinematic chains with two arm links and three links. If there were suppose an n link problem, it becomes very complex. The visualization and the geometric analysis of such a kinematic links becomes very problematic. because the number of joints increase. So like you had here, say x1 y1 x2 y2 xy, you will have n number of points, xn yn xn minus 1 yn minus 1 etc. And instead of one more problem that one might face if they are working with a n-link kinematic chain. So in a 3-link kinematic chain, our assumption was that the operation of the kinematic chain is in 2D, is in xy plane. In a multi-link kinematic chain, it might not be the case. There might be some kinematic links which are in xyz direction, which are in xz plane, whereas some links are in xy plane. And in such a problem, the analysis becomes very difficult. So in such conditions, and every joint, there are different general methods so that the analysis becomes easier. One such generality is that every joint is assigned a coordinate frame. So if this is a joint, depending upon how it is acting, the coordinate frame is assigned, and this is also assigned a coordinate frame, wherein z is the assumption is that everything is operating in xy, whereas the joint is moving along z. So the rotation of the joint is in z. And joint and links are defined by the relative position and orientation of these frames with respect to each other. To simplify this problem, there is a method, there is a term called as Denavit-Hattenberg parameters. Now these people, they found that they found a way to simplify such a problem where using 4 parameters, and these 4 parameters are called as Denavit-Hattenberg parameters. These 4 parameters consist of 2 joint parameters and 2 link parameters. Using this these 4 parameters, the whole problem can be explained. Now the notation is that the links can go from 0 to n. The 0th link as the fixed link if it's an open kinematic chain, and joints can go from 1 to n. And basically the ith joint is between I minus 1 and I minus 1 and I. This is the ith joint. The DH parameters again are 4 in number. The link parameters are link twist angle, which is the angle between the z-axis of I minus 1 and the z-axis of ith link about the x minus 1 axis. So if this is the zi coordinate, and this is the zi minus 1 coordinate, if you just shift it, you can get the angle alpha I minus 1. The link length, which is I minus 1, is the distance between the z coordinate zi minus 1 and zi axis along I minus 1 axis. So if this is zi minus 1 and this is the x-axis for the respective problem, this is zi, this is zi minus 1. So a perpendicular to, if you would draw perpendicular to this, you get xi. This particular line is xi. And So the distance between this and this becomes a minus 1. Okay, let me just clear up stuff. So if this is zi and this is zi, this at a right angle is xi, whereas if this is zi, something like this would be zi minus 1, xi minus 1, sorry. But we are considering the link length as ai minus 1, which is the distance between zi minus 1 and zi. So this and this, if these two coordinates are cutting the x-axis at 2 points, the 2 points of cut are considered as the link length. Next is the joint offset, or di, which is the distance between xi minus 1 and xi along zi axis. So this is the zi axis, this is the perpendicular for xi minus 1, and this is the perpendicular for zi. So you have this and this becomes di minus 1, which is the joint offset. The next parameter is joint angle, or theta I, which is the angle between xi minus 1 and xi about the zi axis. So if you were to transfer this here, this angle becomes your joint angle. So accordingly you can determine the DH parameters for two of the simultaneous joints and the links. Once you have the DH parameters, you can represent it using a homogeneous transformation matrix. Also, the assumption with DH parameters is it is for manipulators with 1 degree of freedom joint, ideally. And once you have, basically they help you represent the position and orientation of link I with respect to link I minus 1, which can be represented as a 4x4 matrix called as a homogeneous transformation matrix, where T, which is basically Ti minus 1 Ti, which is the transformation of link I from with respect to link I minus 1. Here this particular red box is which is a 3x3 matrix, is the rotation matrix, which indicates the orientation of the which has the which has terms related to theta I and alpha I minus 1, which is the link twist angle and joint angle. So all of the angular terms come here. The other one is a 3x1 vector, which is a position vector, which has terms pertaining to I minus 1, di, the link length and the joint offset and the link twist angle. These terms can be used to indicate the change in position. Now, the goal of forward kinematics, as we saw in a 2R and 3N problem, is to obtain the position and ideally with the position the signs and therefore the orientation of the end effector with respect to the base or the origin. If we need to analyze the same for a n plus 1 link, we need to obtain a transformation matrix T0n, which is the transformation matrix of nth link with respect to the 0th link. So this can be obtained by multiplying the homogeneous transformation matrices from t01 to tn minus 1 tn, and the multiplication is always in this direction. If the multiplication in this direction, even though the final magnitude, if computed, be the same, the vector map that we'll get is not the same. Okay. So all the problems that we have seen till now are static. There is no velocity to it. But in actuality, that is not the case. There will always be a velocity component when there is a change in the displacement. So velocity is the rate of change of motion, of position, which is basically dx by dt, and can be represented as x naught. And for objects in rotatory motion, uh, velocity at any point at any instant is tangential to its path of motion. Suppose this is the center and there is an object moving like this. So at any point, it's the tangent which gives us the velocity. Consider a link AB where A is the fixed point, rotating at an uniform angular velocity theta naught, basically d theta by dt, where theta is the angle that AB forms the horizontal. And we need to find the velocity at the tip at point B. And we know that this length is L sine theta and this length is L cos theta. So if dB by dt L cos theta, d by dt L cos theta. Okay. Now this term can be written as Vx. So Vx is equal to L d by dt cos theta, which is L minus sine theta. The differential of cos theta is minus sine theta by d theta by dt. L minus sine theta, theta naught. Vy is L d by dt sine theta L into cos theta, theta naught. So this is how you can describe the motion of the velocity of a point B if A is fixed. So this was essentially a 1-hour problem. Now coming to a 2-hour link chain, where you can write x in this form and y in this form, and therefore this and this. So dx by dt, basically apply differential to both of these sides, you get dx by dt is equal to, L1 is constant, L1 is not changing, so we don't need to consider it in the differential. Differential of cos is minus sine theta 1 dot plus L2 minus S12. Because it's it's theta 1 plus theta 2, you need to take differential of both these terms. Theta 1 naught plus theta 2 naught. So this essentially becomes minus L1 S1 theta 1 naught minus L2 S12 theta 1 naught minus L2 S12 theta 2 naught. Similarly, y naught can be written in this form. So you know what x naught and y naught is. If you want to represent it in matrix form, where v is x naught, y naught, you basically take out this term, separate out this term, and take out this term and this term. Sorry, this term and this term. And you can write it in form of a matrix, and this particular matrix is called a Jacobian, which you can see here. This particular matrix is called a Jacobian. This is the joint velocity or the angular velocity, and this is the end effector velocity or the change in the position. And basically, Jacobian matrix provides an geometrical map between the joint motion and the end effector motion. How the link is moving in a rotatory motion, and how that rotatory motion translates into the change in the position. It is basically the partial derivative of the position vector with respect to a joint angle vector, and it in a nth term it can be defined as this. For a 2R system, this becomes the Jacobian matrix which we saw, and the partial derivatives can be written as this. And so basically dx by, I'll solve for one of the terms. We know x to be this. Since there is no theta 2 component in the derivative, the theta 2 component, so d by dt of a constant becomes 0. So here just d theta 1 by dt remains, and this is essentially what you get here. Similarly, in the when you are drawing a derivative against theta 2, this particular term becomes 0. Okay. Let's look at the velocity analysis for a 3R system, where we know the distance to be to the x coordinate to be L1 C1, L2 C12, L3 C12, y coordinate to be L1 S1, L2 S12, and L3 S123. So if you were to write the derivative of x dx by dt with time, basically d by dt of L1 C1 plus L2 C12 plus L3 C123, which becomes L1, and d by dt of C1 it becomes minus S1 plus L2 d by, and since it's S1 it becomes theta, one sec, S1 d theta 1 by dt plus L2 minus S12 d theta 1 by dt plus d theta 2 by dt plus L3 minus S123 d theta 1 by dt plus d theta 2 by dt plus d theta 3 by dt. This is what it ends up in. Now if you arrange around the terms, take all the theta to one side, it becomes minus L1 S1 minus L2 S12. Take this term out, this particular term, minus this term L3 S123 into theta 1 plus minus L2 S12 minus L3 S123 theta 2 plus minus L3 S123 theta 3. This term becomes the first term in your Jacobian, this the second, and this the third. Similarly, when you compute dy by dt, you get such an equation, where this term becomes the fourth term, this is the fifth, and this is the sixth, and this can be represented in a 3x2 matrix. So we can compute inverses for different for a square matrix. Computing a inverse of a 3 cross 2 matrix is difficult. It's not possible. But mostly when you solve problems, you will encounter problems which are not forward kinematics, rather they are inverse kinematics, where you know the positional values but you don't know the angles. So in such a scenario, the joint angle velocities can be calculated for a desired end effector velocity, and therefore you need to develop a pseudo inverse in such a case. This pseudo inverse is known as a Moore-Penrose pseudo inverse for the Jacobian. The Jacobian inverse is transverse of Jacobian, and which is multiplied by the inverse of Jacobian, with inverse of a product of Jacobian into the Jacobian transverse. So essentially it becomes this is not an exact inverse, it is a pseudo inverse. It's not a true inverse, but for analytical purposes this works. I will let me just pull up the questions. So the first, we can discuss some questions. I'll discuss some questions, and then that's the end. The first question is, how is the radius of the inner circle in the 2R chain workspace calculated? So if you remember, L1 and L2, A, B, sorry, A, B and P. So this is L1, this is L2. The inner circle is basically the lower limit of the workspace, which would happen if assumption is L1 is greater than L2. If this is AB, BP folds over on AB. So P is somewhere in the middle. So this essentially is your length, which is L1 minus L2. Or in case BP is the larger arm, you can get L2 minus L1. So the lowest radius that you will get is modulus of L1 minus L2, which is this answer. What is the mobility M of a kinematic chain having 4 joints and 5 links? If you remember, the mobility is 3 times n minus 1 plus 2j, where n is the number of links and j is the number of joints. 3 into 5 minus 1 plus 2, sorry, minus 2, 2 into 4, 3 into 4 minus 2 into 4, 12 minus 8, 4, and the answer is 4. The workspace of a 2-hour serial manipulator is a region between two concentric circles, area between two parallel lines, a circle of radius L1 plus L2, or an ellipse with the major axis L1 plus L2. So if this is your, so the minimum is here, whereas the maximum is somewhere here, where you get a straight line essentially. So the answer is the region between two concentric circles. The inverse kinematics for a 2-hour plane serial manipulator will yield one unique solution, two solution, infinite solution, one or two solutions. So remember, when we looked at the 2-hour problem, we found a single solution. So the answer, when we looked at the 2-hour problem, we found that there was a plus or minus sign. So essentially there is an upper arm and a lower arm. Therefore, there are two possible solutions. Choose the correct Jacobian matrix for a 2-hour serial manipulator. So the Jacobian was L1 S1 L2 S12 minus so if you go to the Jacobian, sorry for the typo, this is not the correct answer, this is, so the Jacobian comes in this form. Forward kinematics for a 3-link planar chain will yield unique solution, two solutions, infinite solution. The answer is unique solution. In a 4x4 homogeneous transformation matrix for a 3D transformation, what does the upper left 3x3 elements typically represent? This is the T you had, and these 4 terms were there. This was the rotation matrix. This is the translation matrix. This is 3 cross 1, this is 3 cross 3. So basically it becomes, the answer is rotation matrix. Calculate the position of tooltip 2R serial manipulator having a theta 1, theta 2, L1, L2. L1 is 10 centimeters, L2 is 25 centimeters, theta 1 is 45 degrees, and theta 2 is 30 degrees. So if you write the x becomes 10 into sine, 10 into cos 45 degrees plus, here the angle that is given is with respect to the horizontal. So 30 degrees is no longer theta 1 plus theta 2. 30 degrees is the actual angle with the horizontal. So for all intents and purposes, we can assume this to be just L2, this to be L2 cos 30. L2 is 25 cos 30 degrees, y becomes 10 into sine 45 degrees plus 25 cos 30 degree. And you compute this, the final answer comes out to be 13.4 and y becomes 31.22. Select all the correct combinations with respect to DH parameters. Link twist angle alpha I is the angle between zi minus 1 and zi about xi minus 1 axis. Link length a minus 1 is the distance between zi and zi minus 1 and zi along xi minus 1 axis. Joint offset di is the distance between zi minus 1 and xy along zi. Joint angle theta is the angle between theta xi minus 1 and xi about zi axis. Except for this, everything else is correct. What is the significance of the last column in a transformation matrix? Rotation angle, shear forces, position vector, and link length. So this particular is a translation matrix which tells us about the position of the system. So the answer, what is the significance? It tells you about the position vector. So we looked at various problems, the analysis of different kinds of 2-link and 3-link kinematic chains, and the definitions of various terms that are associated with all of this, such as Jacobian matrix, DH parameters, etc. Thank you.